Welcome to Ask and Learn.
So they want us to show that any non-empty finite subset of a lattice has a least upper bound and a greatest upper bound. So normally when we start to talk about things of finite sets, it's normally not a bad idea to try induction on it. So let's see if that'll work. So let's see if we can just get a base case, or first we should come up with a statement. All right, so if this is true, so this will be our induction hypothesis, if this is it. So this is going to be Pn being that x1, x2, dot, 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 all the way up to xn, a subset of our lattice, has a greatest lower bound and a least upper bound. So let's check our base case just to make sure. Because remember, if the base case doesn't hold, doesn't matter. So base case is going to be n is equal to 1. Okay, so that's going to just be x1, and well, the greatest lower bound of any element is itself, and the least upper bound of any element is also itself. So our base case checks out. So now let's figure out what we want to show. So we want to show for our induction proof to hold that Pn plus 1 is true, which is the statement x1, x2, dot, 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 all the way up to xn, a subset of our lattice has a greatest lower bound and a least upper bound. So that's what we want to show. So let's go ahead and start the proof now. All right, so proof. So we can tell the reader that we're doing this by way of induction. So we want to assume, that the statement Pn being x1, x2, x3, dot, 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 all the way up to xn, a subset of our lattice has a greatest lower bound and a least upper bound. All right, so now what I'm going to do is define the following. So let G be equal to the least, or the greatest lower bound of x1, x2, dot, 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 all the way up to xn. And let's also let L be equal to the least upper bound of x1, x2, dot, 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 all the way up to xn. All right, so we have that now. So let's go ahead and start by, actually, we can break this up into two different things like this. So I'll just go ahead and go straight down the middle like that. So over here, now let's take the greatest lower bound of x1, x2, dot, 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 all the way up to xn, xn plus 1. Well, notice that this right here, this is essentially our statement Pn. So what this implies, so this is going to be equal to the greatest lower bound of G with xn plus 1 by our induction hypothesis, and this greatest lower bound exists by definition of lattice having a greatest lower bound for all pairs of its points. So we have that one done. Now, what about over here? So we'll apply that same logic. So we now want to look at the least upper bound of x1, x2, dot, 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 all the way up to xn plus 1. So now, again, this right here is just our statement Pn. So this is going to be equal to the least upper bound of L and xn plus 1. And again, this least upper bound exists by definition of lattice having a least upper bound for all pairs of its points. All right, so we proved both of that. Now we should just kind of conclude what we've shown here. So since Pn plus 1 is true, assuming Pn is true, then we can say that Pn is true for all n elements of the natural numbers. So then we can go ahead and put our little proof box and a smiley face because we're glad we're done with it.